Let me start by thanking the organizers for the invitation. So I will echo Ronald's comments yesterday. This is my first time at this conference, and so I feel like an outsider, yet I also see quite a few colleagues from quantum optics, and I'm enjoying the conference very much. So what I'm going to tell you is the considerations that one faces when one tries to realize a solid-state spin-photon interface. Now, there are quite a few parallels between what I'm going to tell you today and what Ronald Hansen told you yesterday, and I try to sort of highlight sort of the differences as well as the common features as I go along. So let me start by giving you a motivation. So the background for this work is the use of single photons to link quantum nodes in a quantum coherent manner. And you can say that there are two basic ways of doing this. One of them would be to create spin-photon entanglement and then distribute the entanglement by using photons and then carrying out Bell state measurements, as we talked about earlier today in the first talk, and in this way generate entanglement between distant spin qubits that have never interacted with each other. And this is the basic underlying feature of the quantum repeater architecture that was proposed by Briegel, Sirac, Zoller, and co-workers. So this is one avenue, and another avenue that one can envision is that one could think about converting the quantum information carried by a confined, a stationary qubit onto a photonic qubit, which then propagates possibly over small distances, linking different nodes of a distributed quantum information processor. And so in this context, again, this is a bit more futuristic, but these kind of ideas or solid-state implementations might become more relevant as one can think about realizing on-chip distributed information processors. So the basic resource that one needs in all these protocols is okay, so there is a slight mistake here. So the basic resource are either indistinguishable single photonic qubits or entangled spin photon pairs. So we already heard about in Joshua's tutorial the importance of indistinguishability in Bell state measurements using beam splitters. So this is more so the case in the type of experiments that I'm going to tell you about, and also in solid state emitters where indistinguishability should not be taken for granted because of the presence of the environment that in a sense tries to measure what's going on with the emitter. So, so what this was meant to do is to specify roughly what I mean by indistinguishability, that the photonic pulses actually have the same spatiotemporal profile, center frequency, and polarization, or any other internal degree of freedom if we are going to say that they're completely indistinguishable. So that also refers to photon number, orbital angular momentum, energy, and what have you. Okay, so that's sort of one class, and what is of primary interest in this talk is the entangled spin photon states. So in this case, the idea would be to use appropriate transitions such that after an excitation and relaxation process, what one ends up with is a maximally entangled state of a localized spin and a propagating photon. And this photon is, again, the states of this photon is distinguished by some internal degree of freedom. H and V could be polarization, as I said. In this talk, they will actually refer to the color of the photon. That is, whether the photon is blue or red. And blue and red in this case actually are two frequencies that differ by 5 gigahertz. Okay, so here is the outline. So I will first tell you about an indistinguishable single photon source, how we assess indistinguishability. Then I will tell you about creation of quantum entanglement between a confined spin and a condensed matter spin and a propagating single photon. And then in the last part, tell you how we can teleport the information from a propagating qubit to a solid state spin. Okay, so solid state emitters, or sometimes referred to as artificial atoms, can be used to realize high brightness single photon sources. So this is one of the reasons that several groups around the world have been pursuing single photon sources. So in contrast to atomic counterparts, you do not need to worry about trapping. You can integrate them into photonic structures and then couple the output to a single mode fiber. And in principle, one can have very high generation rates that in principle, using cavities, one can envision generating 10 to the 9 photons per second, and with the coupling efficiency of 70%. So in reality, what has been achieved, the maximum numbers I know are about 2 times 10 to the 7 photons, with an efficiency, again, on the order of 70%. So these numbers are on the order of magnitude larger than what you can achieve with atomic systems, and yet retain the high degree of elimination of 2 or more photon events in a single photon pulse. Now, I only listed the bright aspects. There are, of course, negative aspects of solid-state emitters, and one that has been sort of commonly referred to is the need for cryogenics, because these sources really are nice sources at liquid helium temperatures. With the advent of cryogen-free cryostats, this has probably become less of a concern, but still the monetary cost is out there. And the other aspect is that good solid-state emitters are not emitting at the telecom wavelength. So one has to worry about up-converting or down-converting the photons if one is interested in long-distance communication. And that comes with a moderate efficiency, one could say. So there are a number of different emitters with different interesting physical properties. So as a physicist or condensed matter physicist, this is of interest to us. So I classify the emitters into 3. The first one are the rare earth atoms embedded in a crystal. So you probably have heard about this in the context of quantum memories. And what is special about these atoms is that they really retain their atomic properties. And the reason is that one is interested in inner shell transitions of these rare earth atoms, which are immune to hybridization with the electronic states of the crystal. So they have the advantage that you have atom-like properties, and here you also have emitters emitting at 1.5 micron. The disadvantage is that these are typically forbidden transitions, and it is therefore more difficult to get high rep rates and indistinguishability. Although there is remarkable work going on in this field by Jörg Brachtrup and Vahid Sandokhtar. So what we heard about yesterday are deep defects in solids. So a good example is the NV center in diamond, but this is one example, and the community is now exploring other possibilities, silicon vacancy centers in diamond, as well as analogous vacancies in silicon carbide, which is a material that is easier to fabricate. So the interesting thing here is that the properties of the emitter has nothing to do with diamond, nor the nitrogen or silicon that you have in there, because of the fact that it is a deep defect. Now, the final thing in this category are the shallow defects, or quantum dots. So in this case, the optical properties that we are dealing with are really derived from the semiconductor, the host semiconductor that is in the background. And probably the main advantage of the system is the fact that it is the one for which fabrication or nanofabrication techniques have been the most developed. And at the same time, it's also the system where the decoherence times are the shortest. So there's always a trade-off in this regard. So as I already said, I think I will basically focus on quantum dots in the experiments that I'm going to tell you. Okay, so here is a very quick introduction to quantum dots. So this is a cross-sectional TEM picture of a quantum dot. It essentially is an island of semiconductor embedded in a higher bandgap semiconductor. Okay, so in this case, this is indium arsenide surrounded by gallium arsenide. And what makes it special is that even though it has a large size, consists of 10 to the 4 to 10 to the 5 atoms, it nevertheless exhibits nicely sort of discretized electronic and Hall states and has a discrete and anharmonic optical spectrum. So if you have a neutral quantum dot, then the ground state is a singlet state. And that is nice if you're interested in generating either single or entangled photons. And I will not talk about entangled photons in the talk. I will briefly mention it at the very end. But in principle, one can think about realizing a nearly deterministic single or entangled photon sources using neutral quantum dots. And the idea is relatively simple. I already told you that it has a discrete and harmonic spectrum. So what you need to do is to come in with the pulse laser that excites the system from ground state to a strongly optically allowed transition. As this transition decays, it emits a photon. And this photon pulse generated in this process is highly controllable, for example, by using the shape of the excitation pulse, and also by changing the emissive properties by embedding the emitter in a photonic structure. So typically, if you don't do anything, if you have a bare emitter, the pulse shape is on the order of 500 picoseconds to a nanosecond. This can be decreased by an order of magnitude and has been in cavity QED experiments. So this is the basic idea. What is important is that as the system decays to the ground state, there is no signature about the generation of the photon that is left with the emitter. So the system is completely disentangled. And if we can, in addition, ensure that there are no phonons, et cetera, are generated in the process, this can become an indistinguishable single photon pulse. And I will come shortly to that issue in a while. So the nice aspect of the quantum dots, as I said, is that because of this shallow confinement and integration in semiconductor structures, we can envision injecting an electron by applying a relatively low gate voltage on the order of tens of millivolts. And if we inject an electron, then we have something interesting, because now the ground state is spanned by it has a two-dimensional Hilbert space, and is determined by the spin state of this electron that you have injected. Now, if you do light scattering in this case, and I will again discuss this in the second part of the talk, then you can actually have at the output, after the decay occurs, a strongly correlated spin photon state or a maximally entangled spin photon state. And that is the sort of the versatility, if you will, of the system in going from one regime to another. So quickly, how the device actually looks. So this is, I mean, in our case, this chunk is really about a millimeter size, but it can in principle be made down to a few micron in diameter pillars, which are actually fabricated in LPN near Paris in terms of the state-of-the-art pillars. So it's a bunch of semiconductor layers for manipulating the photons, as well as having electronic layer, electron dope layer to inject electrons, and you insert everything inside either a liquid helium bath cryostat or a cryogen-free cryostat, as I alluded to in the beginning of the talk. So let me then sort of tell you about characterization of what we generate. So now I'm considering a neutral quantum dot. We're generating single photons. So I excite the system, it decays, and it generates these photons, say, in a periodic manner. So we want to show that what we are generating never contains more than one photon. And the way to do that is to use the Hanbury-Brown twist setup. So this is, as you can see, it's rather similar to what we have seen in Joshua's talk earlier. In this case, we send the photons through one port and then use a 50-50 beam splitter to split the output into two arms. And here we have single photon detectors that essentially click generate a voltage pulse as soon as they detect a photon. Now, what the electronics does for you is to monitor the waiting time distribution between the clicks, and in this way determine the correlation function, the intensity correlation function of the incoming light source that you want to characterize. So if you want to use a attenuated laser beam, a weak laser pulse that has a number of photons on the order of 1, as you've been discussing for the QKD protocols, then what this measurement will give you is that all the peaks that are separated by the repetition rate of your excitation are going to have the same magnitude. And basically what you're finding here is that if you detect a photon, if it has a Poissonian distribution, you get absolutely no information about the likelihood of detecting the second photon, and that is as likely in this pulse as it is in the following pulses because of the, let's say, the renormalization of the wave function. So this is what you would get with the Poissonian light source. And if you use the output from a single quantum emitter in a quantum dot, what you can obtain is a very strong suppression of these 2 photon events, 2 or more photon events in the center pulse, indicating that the likelihood of having 2 or more photons is on the order of 1%. And this is actually an experimental result from LPN, and this is the signature of single photon source that we typically use in our experiments, but it's also common for NV centers and rare earth atoms, etc. So that's the story with the single photon. But as we heard earlier today, an important feature, if one is to realize a Bell state measurement using a beam splitter, one needs to ensure that the photons are indistinguishable. And the very same beam splitter that we would use to realize the partial Bell state measurement, we can actually use if we take on this hat as being the physicist or the engineer who's trying to realize these sources. We can use the same setup to characterize how indistinguishable our photons are. Okay, so we send the 2 photons onto the beam splitter, and indeed what we will find if we adjust the emission frequencies of our emitters and set the polarizations of the photons to be identical, that the coincidence counts denoted in the red is on the order of 10%, whereas if you change the polarization, then the coincidence probability is 50%, since the photons are now distinguishable and will not exhibit 2 photon interference. Okay, so what I would like to highlight here is that indistinguishability is really, or these kinds of measurements are nice because they really tell us that the single photon pulse that we are dealing with is really not entangled with any other degree of freedom, right? So if we really get this level of sort of suppression, then we know that we have pure photons and information about the emission time or the energy or what have you is not contained in another reservoir or in a measurement setup. Okay, so what we did is we used a quantum dot to generate such single photon, indistinguishable single photon pulses. Actually, as I already said earlier, the degree of freedom that we use in these experiments is the energy degree of freedom. So we actually use the fact that there are 2 close lying excited states of a quantum dot, which these are called the fine structure split excitonic lines, and the splitting ranges from 5 to 20 gigahertz. So we do a simultaneous excitation of these lines, and as the system decays, or after the decay is completed, the system is in, the quantum dot is in the unique ground state, and we have generated a photon, but this photon is in a superposition of the blue and red colors. So if we then do a measurement where we map out the photon pulse shape, we see that this has these beats arising from the fact that we have these 2 colors, and the beat frequency is indeed the frequency difference between the 2 excitonic states. So now I show you here the single photons generated by 2 different quantum dots sitting in different cryostats that are 5 meters away. And what we do is that we use the benefit of these mesoscopic devices that allow for electrical and magnetic control of their emissive properties. So we apply electric and magnetic fields. We start out from different quantum dots, Because of the random formation, which I did not mention, each quantum dot is different. But what we really realized over the last few years is that even though we start out with different dots, we can bring them or make them identical in the sense that the photons that they emit become indistinguishable. Okay, so and that's what I will show shortly. So this is after our efforts to make sure that the two quantum dots are identical in terms of their emissive properties. This is the G2 measurement, intensity correlation, showing that both dots still emit mostly one photon with a few % probability that there are two or more photon emission events. Okay, so then we send these photons onto a beam splitter. And indeed, what we see is similar to what I've shown you before, with slightly more complicated profiles coming from single and two photon interference and beats that arise from the frequency difference. So this is when the photons have parallel polarization versus orthogonal, if you instead choose orthogonal polarization, or if you delay the arrival time of the pulses, then they become distinguishable, and you recover the coincidences. Okay, so that is all I want to tell you about the single photon part. So now I would like to inject this electron that I mentioned earlier and look at the system where one can study spin-photon correlation. So the energy level diagram, from sort of a simplified energy level diagram, changes. Now, as I said, we have two ground states, the spin states of the electron, and we couple to two excited states. Now, how these couplings are actually depends on whether we put the quantum dot growth direction in line with the magnetic field or rotate it. So first, I want to show you what happens in the so-called Faraday geometry where they are aligned. Okay? So this is important for spin measurement and initialization. So what happens in this case is that we have these quasi-recycling transitions that if I apply a sigma plus laser that only talks to the spin up state and a sigma minus laser only talks to the spin down state. So in this way, just like what is done in trapped ions and to some extent in NV centers, we can scatter photons and get information about the spin state. And this is then such a measurement. We prepare the system in spin down using optical pumping. Then we apply a pulse that is 0.8 microsecond and then count the photons. So if we prepare, I should have said it this way, we prepare it either in spin up or spin down, but we only apply our laser on the spin down transition. Okay, so if the spin is prepared in spin down, we have counts, and if it's prepared in spin up, then we have no counts. And this gives us a single shot fidelity of 80%, which is actually substantially lower than what Ron was showing, but this is a system without a cavity, no photonic structure. So in principle, this can be boosted up to similar levels. Okay, so now for spin photon entanglement, we rotate the magnetic field. In this case, the selection rules change, and I will not go into details of this at all, but we still again have two initial spin states. But now, when we excite the system, it has equal probability for going down to either spin up or the spin down state. And if you do not observe either the spin or the photon, then at the end of this excitation process, what we have is an entangled spin photon state where entanglement is both in the color and the polarization, because actually this photon is vertically polarized and this is horizontally polarized. Okay, so what we then do is to erase the polarization information. We use a polarizer set at H plus V, and then study the properties of the color photonic qubit and the spin and measure their correlations. So this is how we do our experiments. So we have a relatively fast repetition rate. We have a pulse that measures the spin and prepares it in the state that we are interested in one go. And then we can manipulate the spin. We apply a shorter pulse to generate entanglement, spin photon entanglement, and then the next pulse is going to measure and prepare it for the next cycle. And in between, we can rotate the spin to carry out measurements in different bases. Okay, so what we do is then first look at classical correlations, and you can see that the photons generated during this entanglement pulse, we can separate the color using a Fabry-Perot interferometer or filter. And here you see that the red and the blue photons have the same shape, have the same single photon pulse shape. And the pulses mostly contain single photons as verified by the G2 measurements. And then if you do a conditional measurement, that is, if you look at the color conditioned on, let's say, detection of a spin down, we see that it's mostly red versus mostly blue if you condition it on spin up measurements. So in this way, we see that we have strong classical correlations between the color of the photon and the spin state. Then we turn to the X basis, or what I refer to as the quantum correlations. So we use an additional pulse here to project the spin either to up plus down or up minus down. When we do so, detection of the spin projects the photon into a superposition of the two colors, which then exhibits the beads in the sense that I have shown you before for single isolated photonic qubits. And these beads are at the spin splitting, and they verify to us that indeed the system also has quantum correlations, and the overall entanglement fidelity is on the order of 67. We have increased this above 70 in the meanwhile. Okay, so a drawback, you can see that these oscillations decay very fast, and that is due to the short T2 star time of the electron spin. So that's a major hurdle that has been slowing down electron spin-based quantum information processing, that there is a random nuclear spin path with an unknown orientation, but this is a quasi-static path, so it's in principle can be eliminated to a large extent by spin echo, but unless you do spin echo, the correlations that you see decay in a fast time scale. So, in the last part of the talk, I will tell you briefly about the teleportation experiment. So the idea here is to combine the two elements that I have shown you before. So we use one quantum dot in a different cryostat to generate a photonic qubit, a photon in a superposition of two energy states. And then in another quantum dot, we generate spin photon entangled state. And we do a partial Bell state measurement on a beam splitter, and detection of coincidences allows us to sort of teleport this state onto the spin state of the quantum dot. And again, I will not show you all the characterization, but this is the X basis characterization. So if you prepare the photon in a red plus blue state, then we see that the coincidences are highest when we measure the spin in the up plus down basis, and these are sort of at different periods. Of course, the photons are or should be uncorrelated, but there is some substantial noise in the measurement. Okay, so the next step for us is to generate entanglement of distant spins, and to this end, we have two avenues to be able to herald the entanglement, which will take about 10 nanoseconds in our case. We either need to do spin echo on the electron spin, or we use another solid state qubit that has a longer coherence time. And we chose the second avenue, so we're using heavy hole spin. So this is, again, I won't go into detail, but there's more than 1 degree of freedom that you can think of using in this system. And this heavy hole spin has a coherence time, T2 star time, of 250 nanoseconds, which is more than 2 orders of magnitude longer. So the idea here is to take two quantum dots, generate spin photon entanglement, and then look at either the single photon click following the proposal of Cabrillo, Sirac, and Zoller from '99 to generate entanglement between the spins in the two quantum dots. Okay, so where this might be going, why sort of bother with this kind of system? I already mentioned that that one nice aspect of the gallium arsenide-based systems is the fact that the nanofabrication technology has substantially advanced. So here is a AFM picture of a photonic crystal containing a quantum dot. So this is a device that we fabricated a few years back, which allowed us to achieve strong coupling cavity QED in a deterministic way for about 5 years. So basically, we could go back to the same device and measure over and over again and show effects like photon blockade, etc. So this is, in a sense, the power of these systems, that you have integration capability. So what is missing here is the directional photon output, but that can also be addressed using photonic crystal circuits. So the idea would be then you have some qubits. It doesn't have to be one, embedded in a photonic crystal defect. The photons are emitted into a photonic crystal waveguide, can be interfered in a beam splitter and detected also on chip superconducting detector. So I'm not so much of a technology person, so you can probably see that in the way I describe it, but there is a vision for having an integrated on-chip quantum information processor, even if it's a relatively modest one allowed by these systems. Okay, so basically what we are going in this project is that we first really want to establish, in a sense similar to what Ronald did in NV centers, that we can have reliable, relatively high rate entanglement between distant spins. To this end, we are considering not only the whole spin that I've shown you, but also other potential long coherence qubits in quantum dots. And the other possibility that one could consider is really to use not just the first excitation, but excitation to a biexciton state in a quantum dot, which can then be used to generate a deterministic source of entangled photons. But there are other challenges that go into this, which several groups, including Andrew Shields' group, have been trying to address. Okay, so that's where I will stop, and thank you for your attention.
Atash, I may have missed it. What is the wavelength of the photons emitted from your quantum dot? That's the first question. The other one is, in your measurements of the G2 autocorrelation functions, your peak at 0 temporal delay was almost down to 0, but not exactly. A naive person like me would expect for one quantum dot you should never get more than one photon, but there's probably something wrong in my naive vision.
So the wavelength of the photons in this case are 962 nanometers. So basically, without sort of having much of a change in the properties, one can have quantum dots ranging from 900 nanometers to 1 micron, possibly up to 1.2 microns. And I'm saying possibly because of the detectors or the lack of detectors up until recently. Not many people looked into these redder quantum dots. Now that we have and you have superconducting detectors and use them, we could in principle go back in this direction. So the reason why G2 is not so good in our case is because of the fact that our excitation pulse is on the order of the spontaneous emission rate. So there is a finite probability that we excite and then the system goes back. So I was showing you G2 in a pulse, which means that G2 of 0 in a CW experiment is 0, you're right. But if you look at the pulse, since the pulse is sizable, then you can have, and this has other advantages. So we need to minimize the bandwidth of the pulse to make sure that we do not excite other states, and that's where it comes from.
You showed that it's teleportation from the photon to solid qubit. Do you see in the outlook that it's possible to do it the other way around?
Yes, indeed. I think that the way to go there would be, for example, that you generate, well, okay, so yes, I don't, so if you're asking me whether I will be doing it anytime soon, the answer would be no. So the idea would then be, or what comes to my mind is this, that I could in principle convert the spin qubit into a photonic qubit and then do a partial Bell state measurement with one element of an entangled photon. So in this way I can realize this. But in principle, it is possible to convert probabilistically the spin qubit to a photonic qubit. The reverse is more challenging experimentally, to essentially generate photonic qubits with the proper pulse shape that will yield unity conversion into a spin qubit. So it's in principle possible, and I believe there are realizations in single atoms in cavities. But in this system, that way, one way is easier. So it's in principle possible.